All right, welcome to part 2 of section 4.1. We're going to hopefully make this pretty quick. So for warm up today, we're going to do a little bit of maybe kind of out of the blue something here. Convert each time measurement into its equivalent number of hours, but in decimal form. All right, so what we're talking about here is 45 minutes is how many hours? That's really the question. And clearly the answer is less than 1. And so the question is, what decimal is it? So instead of converting into minutes, let's just leave it as like a fraction or a decimal of an hour. And the answer then, of course, is going to be there are 45 out of a total of 60 possible minutes. And so we're looking at 3/4 of an hour, right? Or 0.75 hours. Excuse me. All right. 36 seconds is how many hours? Now, I could jump straight to hours from seconds if I give it some quick thought, but we might as well just walk ourselves through it for a second. And let's, instead of figure out how many hours it is, let's figure out how many minutes 36 seconds is. Obviously, it's a little bit over half of a minute. So what's the answer? Well, the conversion is exactly the same because there's 60 seconds in a single minute. So I have 36 seconds out of a total of 60 seconds, which gives me the fraction of 36 over 60, which is going to be 6/10. So that would be 0.6 minutes. But I don't want minutes, I want hours. So the question now is how many hours is 0.6 minutes? And the answer is not very many. But what do? We do the same thing we did on part A. We're going to take our 0.6 minutes and we're going to divide it by 60 possible minutes. And then I get an answer of 0.6 divided by 60, which is going to be 0.01. So 36 seconds is equal to 0.01 hours. Now, those of you who are pretty good at math will be probably sitting like Mr. Mueller, why didn't you just take 36 and divide it by 3,600? Same answer, because you're dividing by 60 and dividing by 60 again. So I did exactly what you're saying. I just kind of stepped through it and I converted one piece at a time. Okay, so then the next question is, all right, then how much is 45 minutes and 36 seconds? Well, we know both the answers already. We know that 45 minutes was 45 out of 60. And we know that 36 seconds ended up being 36 over 3,600. And we ended up getting 0.75 plus 0.01, which is 0.76 hours. Now, that's all good and fine because we just did that math. But what if we had just asked you this question to start without doing any of the lead in? Then here's how I would have approached it. I would have said, just like I did before, 36 out of 60 is how many minutes? And I would have got that that's 0.6 minutes. Then what I would have done is said, okay, so I don't have 45 minutes. I actually have 45.6 minutes. I would have combined those together and then done that divided by 60. And then 45.6 divided by 60 is going to equal 0.76, which is the number of hours we have. So that is how we do these problems. All right. Now, why are we talking about this? Well, because there is a measurement in angles that uses the phrase minutes and seconds. And I want you to think about this for a minute because there is some logic here that if originally 360 degrees was used based upon time, right? We use 360 degrees in a circle because it was estimated thousands of years ago that there were 360 daytimes and night times in 1 year. And so if you continue with that theme of time, then minutes and seconds seem a little bit more logical. All right, so what do you need to know? A degree is pretty small. So if I take a single degree, it's going to be, and this is not even going to do it justice, a single degree is a very small amount. And this is more like 10 degrees, but we're just going to pretend. So let's pretend like this is about 1 degree. So what we have done here is we're going to take our 1 degree and we're going to actually refine it and be even more precise. Just like we don't just talk in hours, we've broken hours down into a subunit. We're going to break degrees down into a subunit as well, and that unit is called a minute. And a minute, just like it is in time, is 1/60th of a degree. So a minute is a 60th of an hour. In this case, a minute is a 60th of a degree. What does that mean? That means if I took this very small degree that's been blown up and I divide it into 60 individual parts, right? Then each of those little tiny slivers would be the size of a minute, 1/60th of a degree. Think minutes compared to hours. Now, what is seconds? The seconds would be if I was zoomed in with my microscope into that little spot right there, and now have this even tinier wedge. That's 1 minute. And I divide that into 60 seconds. That is how much a second is. 1/60th of a minute. It's the same exact thing we do for time. It's just been converted and used in terms of degrees. So the answer and the math that we do here will be exactly what we just did. So how big is 18 degrees, 30 minutes, 18 seconds? This is minutes. This is seconds. Well, we're going to step through this a little bit at a time. So I know that there are 18 out of a total 60 seconds. And that is going to equal, I could probably just do this in my head, but I've got a calculator. I'm going to use it. 18 divided by 60 is 0.3. So that's 0.3 minutes. So I'm going to combine that with my 30 minutes. So now I have 30.3 minutes. And divide that by a total possible 60 minutes. So let me add 60 to my, add 30 to my previous amount. So 30.3 and divide it by 60. Obviously a number very close to a half. And I get 0.505, which is hours, but we're now just going to say that's degrees. So we have 18.505 degrees. 72 degrees in 9 minutes, 36 seconds. I've asked you to try this without a calculator, so I haven't said it again in this video, but please pause and do these on your own. So 36 seconds out of 60 seconds, I can reduce that fraction into 6/10 or 3/5. So that's 3/5 of a minute. But I have 9 3/5 minutes divided by 60, which is going to be 48/5 over 60, or 48/5 times 1/60th. Let's see, 12 goes into 48 4 times, 12 goes into 60 5 times, and so I end up getting 4/25. So what's the answer? 72 whole degrees and 4/25 of another degree. All right, and finally, the last one. 51 out of 60 is equal to, divided by 60 equals 0.85. 19.85 over 60 add 19, divide by 60, and 0.33083, looks like repeating after that. So I'm going to say approximately equal to 101.3308 degrees. All right. So again, degrees, minutes, and seconds is simply a way of further giving specificity to the size of an angle. Just like we don't talk just in terms of hours, we broke that into minutes and we broke that into seconds. For time, we do the same thing with degrees. You'll find this most common when we're talking about navigation, which is something we'll do a little bit later in another chapter. We will use these symbols in this notation when talking about bearings of ships and things like that. Okay, example 1. Let's now go the other way. Let's convert from degrees, minutes, and seconds from just degrees. So in other words, let's figure out 0.65. We know the answer is 22 whole degrees. But what is the 0.65 going to do? Well, if we divide by 60 to find the decimal, we're going to then realize that we are multiplying by 60 to get the minutes and seconds. Because you have 0.65 of what? You have 0.65 of another hour, but another hour is 60 minutes. So all we're going to do is take our 0.65 and multiply it by 60. 65% of another whole hour or 60 minutes. So 0.65 times 60 is 39. No decimal, so we don't have seconds. This is an exact 22 degrees, 39 minutes. So 22 whole degrees and 39 little wedges of the next degree. All right, 15.15 of a degree, so 0.15 of 60 minutes. 0.15 times 60 is 9. So we're talking about 9 minutes. So this is negative 120 degrees, 9 minutes. And finally, 0.08 of an hour, or of a degree, 0.08 times 60. We get 7 degrees and 4.8 minutes. But we have a way of being more precise than 0.8 minutes. We can go down to seconds. So 0.8 minutes is 0.8 times another 60. So we have 0.8 times 60, and that is 48. So we have 7 degrees, 4 minutes, and 48 seconds. All right. And changing gears a little bit, we're going to talk about a little review from geometry. We've got arc length. For reasons I'm not sure of, arc length is traditionally labeled with a variable of s, which is not my favorite because my s's sometimes look like 5s. But that is what is traditionally done. So if I want to find the length of an arc, then my strategy here is going to be pretty straightforward, and we learned this in geometry. The S, the arc length, is just a portion of my full circumference. So my job is to figure out what portion. Well, it's going to be the same portion that the angle is making up of this whole circle. So in other words, arc length is simply going to equal the fraction of the circle we're talking about, which can be found by doing the angle divided by 360 degrees. And now we know what fraction of the circle we're discussing. And then what am I going to do with that? I want the fraction of the circumference, so 2 pi r. So for this problem, we don't really need we can kind of already tell it's just 1/4 because of the 90 degrees. But if you didn't realize it, then it's just 90 over 360 times 2 pi times 10, which is going to give me 1/4 times 20 pi. So arc length is equal to 5 pi centimeters. If you want a less exact but maybe more useful number, then I can just, of course, do 5 times pi. And I'm talking about an arc length of approximately 15.708 centimeters. All right, part B, we're going to do the same thing. The arc length is equal to the portion divided by the total of the circumference. So S equals 65 over 360 times 2 pi 10. So that gives me what? 65 over 360 times 20 pi. I can just grab my calculator, or I can do a little thinking. Zeros cancel. 2 over 36 is 1/18. This appears to be 65 pi over 18 centimeters, which, if I grab my calculator, I get 65 divided by 18 times pi. So this is the exact answer, and the approximate answer is around 11.345 centimeters. And we'll do one more for good measure. Except this time, you'll notice I've given you the angle measure in radians. So if we think about our process here, again, arc length is theta divided by 360 degrees times 2 pi r. That only makes sense if you're talking about theta in degrees. The 360 degrees doesn't make a lot of sense if we're talking radians. So let's now talk about how this would change with radians. Well, the concept is the same. The arc length will equal the portion divided by the total, but now the total is 2 pi. In one circle, there's 2 pi, so you've got theta over 2 pi times the circumference, which is 2 pi r, which you'll notice, regardless of what happens next, the 2 pi and the 2 pi cancel out, and you're left with the arc length that's simply equal to theta r. And this is just one additional example of where radians and math with radians is much easier. So I'm not going to go into a whole big thing right now connecting the dots here, but it shouldn't take much for you to realize that since radians are already defined in terms of arc length, right? Or 1 radian is defined as the arc length when the radius and the length of this are. Let me say that again. When the radius and the arc length are the same, then that means that S, the arc length of what we're talking about in question, is simply going to be the angle times the radius. It's been a long day, so I'm not going to elaborate on that right now. But if you have questions, definitely come talk to me about it. So let's find the answer in this case. S equals, the angle measure is 7 pi over 10 radians times 14 centimeters. And we can do a little bit of reducing here. 14 tenths is 7/5. So the arc length in exact terms would be 49 pi over 5 centimeters. Or approximately, I think it's 30 point something when we do the math here. Let's find out. 49 divided by 5 times pi. Approximately 30.788 centimeters. And if we had decided to convert this into degrees first and then use the other formula, we would get an answer very much the same, but with a heck of a lot more work. All right, and the last thing we're going to do here is just do the same problem, but now in reverse. So given a situation where we know the arc length and we know the radius, what is the angle? So we're going to do this in terms of radians, and maybe we'll take a second and do it in terms of degrees to show you how much easier one is than the other. So once again, like if you kind of forget what was the shortcut, it's really easy to figure out that we know that the arc length is the angle measure divided by the total angle measure, 2 pi, times 2 pi r. Oh yeah, that just cancels out, right? That's always going to be the case. But if you don't memorize it, you can still get to the same spot very easily. So the arc length of 28 inches is simply equal to the unknown theta times 10 inches. So I divide by 10 inches and I get that theta is equal to 2.8. And remember, that's in radians. Not 2.8 degrees. Obviously, our picture does not look like 2.8 degrees, but it does look possibly around, and this is, of course, not to scale. That's about 2.8 radians, right? One radian is about 60 degrees. Another radian is about another 60 degrees. There's your second radian. And then there's your 0.8 radians. So 1, 2, 0.8 radians. Okay. Radians, again, normally are written in terms of pi, but they don't have to be. Theta is equal to 2.8 radians. You don't need the radians. I'm just doing this as a reminder. The same problem in degrees is a lot more involved. Not hard, but a lot more math. That would be S equals theta over 360 times 2 pi r. So 28 equals unknown over 360 times 2 pi 10. And now I've got to do a lot of math. I got to multiply by 360 on both sides and divide by 20, right? And so, and divide by pi. So getting theta in degrees is a heck of a lot more work. All right. So that's it for 4.1. If you have questions, let me know.